session, first session. This is on 3D printing of metals by Professor Adeppu Kumar. So I am introducing you. Professor Adeppu Kumar has completed his diploma in mechanical engineering from Government Polytechnic Warangal in the year 1991 and BTech Mechanical from Kakatiya Institute of Technology and Science Warangal in the year 1995 and MTech Production Engineering from SU University Tirupati. He did his PhD from Usmania University in the year 2008. Dr. Kumar initially joined as lecturer in KITS Warangal in the year 2000 and served as lecturer and senior lecturer in the Department of Mechanical Engineering up to 2008. And later he was selected as assistant professor in the Department of Mechanical Engineering, NIT Warangal, in the year 2008 and was promoted as professor in the year 2018. He has more than 20 years teaching experience and 12 years of research experience. His research areas includes additive manufacturing, friction stir welding, modeling of friction stir welding process, fabrication of composites by casting process, and electrical discharge machining of titanium and superalloys. He has guided 8 PhDs and 6 are under progress. To his credit, he has published 65 papers in highly reputed international journals. He has completed 3 projects worth of 30 lakhs and 1 project is ongoing worth of 19 lakhs. He also has, to his credit, of presently handling 2 international projects under India, Belarus. He has filed 2 patents. Dr. Kumar is reviewer for various journals. He has delivered lectures related to friction stir welding process, advanced manufacturing process, and design of experiments at several conferences and workshops. He is also fellow of Institute of Engineers, India, and also life member of various bodies like MIST, MIWS, MSQAR, and MIIW. He is awarded IIM SAIL Gold Medal 2018 as one of the co-author of the technical paper. He wrote 1 book chapter. He has executed various administrative responsibilities. He is BOS member of various institutions. He is serving as member in various committees, and he has also conducted various short terms and workshops. So with this brief introduction of Professor Kumar, so I am handing over the proceedings to Dr. Kumar to proceed. Professor Kumar, over to you.
Yeah. Thank you, Dr. Y. Ravi Kumar, introducing me to the today's lecture. So, good morning to all of you. I'm audible to everyone.
Yes, you are audible. You are audible.
Yeah. So today my talk is on 3D printing of various materials. Introduction to additive manufacturing that may be covered in last lectures. I'm not going to much focus on introduction to additive manufacturing. Then I'm classified into 2 areas. One is beam-based additive manufacturing. So in that I'm going to talk on more on direct energy deposition process and powder bed fusion process and hybrid manufacturing process. And other classification, non-beam based additive manufacturing, the friction stir additive manufacturing, additive friction stir deposition, and some topic on lattice structures by wire arc additive manufacturing with brief only. So basically any manufacturing process categorized as in 3 areas. One is subtractive, additive, and formative process. Then subtractive process, you have to remove the material from the stock and you need to develop the product. And additive process, you are adding the material layer and finally you are going to achieve a final product. And formative process, just you are changing the shape from initial to uniform to the without changing the reduction in volume or why echo is coming? YRK.
No, you carry on. Actually, whenever these people will come, so they will open that microphone. Carry on.
Okay. Right. Oh. So additive manufacturing is a manufacturing process in which functional parts can be made by adding materials without using special tools and fixtures. Without using of these tools and jigs and fixtures, you can have a lot of advantage in terms of reduction in lead time, less wastage, and cost independent of complexity materials. Basically additive manufacturing in 8 steps. One is CAD file, STL file conversion, and file transfer to machine, and machine setup, build up, and remove the material from the substrate, and you can do post processing and applications. Then coming to the difference between computer numerical control machine and additive manufacturing with respect to material and speed, complexity, accuracy, and geometry and programming. Suppose if you see this picture, this cup is made up of ceramic material, which is not possible by in CNC machining process with good accuracy as well as good geometry. Whereas an additive manufacturing, we can able to produce the component very easily, even ceramic materials also. So with respect to complexity, if you want to generate the different cooling channels in electronic devices, because of its complex nature, CNC is not suitable, and you cannot get the accurate shape and size of the channel. Once you apply this same techniques to additive manufacturing process with respect of any complexity, because you are divided into STL file, that STL file is the combination of each and every geometry, then you can able to produce the component very easy. Then coming to accuracy and the geometry point of view, accuracy is very fine in CNC machine compared to AM machine, because some problems encountered during the certification process of the additive manufacturing process that leads to inaccuracy, not much equal to the accuracy what we are getting from CNC machines. Similarly, geometry also a little bit lighter than CNC machine. Then coming to, I'm exposing on CNC, we can call it as a 2.5D process, whereas additive manufacturing 3D process. So what is the difference between 2.5 and 3D is you can able to generate the object in additive manufacturing without any secondary step. Secondary step is required, whereas CNC, if you go for 3D object, is not possible to without adding any secondary step. That is the difference between these. Then you can save a lot of time when you are applying the additive manufacturing production of any components. This is the time you are going to save through additive manufacturing process. Then just you can see this diagram, injection molding versus various additive manufacturing components produced by the various processes with cost and the production volume. So there is a break-even point between the injection molding process as well as other additive manufacturing process. The break-even point where before the break-even point, at left side of the break-even point, injection molding process is very costlier than any other additive manufacturing process. After break-even point, because you are producing the more number of components with the use of single machine, so the cost is divided into number of components, so that the cost is reduced after break-even points. So based on your production volume, you can decide which process is suitable for the production of the components. The various applications I'm not going to detail, because you can find so many applications already discovered. This is aerospace applications. Now coming to direct energy deposition is an additive manufacturing process which focused So which focused thermal energy is to fluid material by melting as they are being deposited. So when you are applying the laser as a energy source, then you can feed the powder with the proper flow rate and at exact the focal point of the laser beam where the maximum energy is available. So that energy is utilized to melting the powder particles and deposit it to the substrate. The binding mechanism, the thermal energy is used to melt the powder particles, and technology fusing materials used as a focused thermal energy source such as a laser or electronic beam. The commercial technologies are available, DMD and laser engineering net shape and style. So it is also an additive manufacturing process used generally for repair and rebuild worn or damaged components to manufacture new components and to apply wear and corrosion resistance coatings. DMD produces full dense and functional parts directly from CAD data by depositing metal powders pixel by pixel using laser melting and patented closed loop control system to maintain dimensional accuracy and material integrity. So with the feedstock 6-axis deposition and multiple material delivery capability, can coat, build or rebuild parts having more complex geometries. So this is one of the energy sources, the electron beam, which we can use for building the components through additive manufacturing process. It is similar to electron beam welding. You have an electronic gun, and it emits the electron when high voltage is applied to the electronic gun. It reaches to thermionic temperature. At that temperature, electrons are emitted. That electrons will travel from the electrode to the target plates through focusing coil and deflection coils. Then you need to maintain a vacuum environment in electron beam welding, electron beam as a energy source for additive manufacturing process, because the electron mass is very, very low compared to the mass of nitrogen and oxygen which are present in the atmosphere. If you are operating in the open atmosphere, the target area is not reached because the electron's mass is very low. Then it is flaring like this. The energy density is very low. That energy is not sufficient to melt the powder particles or electric wire which are used as a feed material. That is not possible to melting the temperature. Then you cannot you cannot able to melt the material, and finally you are not going to achieve a better mechanical properties of the additive manufacturing process. So here I'm showing the electron beam as a source and a laser beam as a source. Now electron beam as a source, yes, you can feed the filler wire through feeder or powder particles also you can feed. Then this feeding location exactly the focal point of the electron beam or laser beam. So there higher energy is available. That energy is utilized to melt the material, and you can deposit on the substrate. This movement of the electron beam is similar to the geometry which is obtained through CNC X and Y axis plotter from the CAD data file. With you can able to generate the different configuration of the components. So here another source is laser. Then laser is passing on to the where the powder is impinging on the substrate. Then the powder particles are melted and deposited on the substrate. The difference between these in this is here the powder is the electron beam as a source. Here electron beam as a source, is a laser as a energy source. So that is the difference. Depending upon the material you are going to use for additive manufacturing components, either you can use the laser as a beam source or electron beam as a source. So this is direct energy deposition process. In the direct energy deposition, your energy is directly impinging onto the powder particles or feeding material. Their melting of the material takes place and deposition takes place. So this is one video just going to show you. This is a laser as a power source, and you can feed the powder particles from the nozzle, and interaction between the laser and the powder particles, and melting takes place. So this is another feeds material is in the form of wire, just you can apply the laser or electron beam, then the material is melted and deposited to the substrate. So this is DED technology, electron beam as a source and or laser beam as a source. Then you can feed the powder particles through different processes. Then you can able to melt the material and you can deposit the material onto the substrate. So you can able to generate very complex geometries, and the difference between electron beam as a source as well as a laser as a source. The first one is a thermal source. So thermal source is an electron beam. Here laser as a energy source. Then atmospheric condition, electron beam required always vacuum, because already I told you, because of the electron mass is very low compared to the nitrogen and oxygen molecules. That's why you need to create vacuum. Then here some of the materials which are active in open atmosphere like titanium and aluminum and magnesium alloys, then you can go for inert gas environment, so that material will not react with the oxygen or nitrogen which are present in the atmosphere, not to form any oxides. That's why we need to avoid those oxide formation. Then you can go for inert gas environment. Then scanning, deflection coil is galvanometer, energy absorption, conductivity limited and absorbed. This one other major limitation electron beam melting process. In electron beam as a source, you can do only conductivity materials, not for non-conductivity materials. Whereas in a laser, you can go for high absorptive materials. We can go with the laser as a power source. Highly reflective materials, we cannot go with the laser as a power source. So here, powder preheating using electron beam, using infrared or resistive heaters, and the scan speeds very fast, magnetically driven, and limited galvanic inertia, and energy cost moderate, and in this case high. Then surface finish, it is a poor and poor to moderate. Then feature resolution moderate and excellent, and metals conductivity materials can be do it in electron beam as a source. Whereas here metals and polymers and ceramics, only highly reflective materials cannot be possible through a laser as a power source. The powder particle size here medium, here you can go with the medium or high or low. So the benefits, you can have high productivity, because you can use electron beam as a high power density compared to laser as a power source. Then you can go for high productivity, and that's suitable for mass production, and no residual or internal stresses developed, because you can concentrate only particular area, and other areas is not affecting that much as in the case of powder bed fusion process. So less supports are required for parts, and possible to stack parts on top of each other, no gas contamination, and very fine structure and good mechanical properties, because you are using a vacuum as a environment in the electron beam melting process. That there will not be any gases, but the gas contamination over a period of time, because of the melting of the material, that forms oxides. So that leads to gas contamination over a period of time, not initially. The drawbacks, conductivity materials can be possible in electron beam source, then powder is sintered so it's tricky to remove. Long dead time between the two production, because every time you need to create a vacuum in electron beam as a source. That's why the long dead time is needed for electron beam melting process. And expensive maintenance cost, because you need to create a vacuum. For that, you need additional vacuum pumps are required to create a vacuum in the electron beam setup. That's why the expensive maintenance cost, with respect to maintenance cost, it is very high. So these the materials which are used for DED process: titanium alloys, stainless steel, maraging steel, tool steels, aluminum alloys, refractory metals, tantalum and tungsten, niobium, and superalloys and rust alloys, nickel, copper, and other specialty materials, composites, and functionally graded materials also. So the benefits, you can have high printing speed, because a lot of energy is available, that you can go up to 11 kg per hour and ideal for repairing parts, especially DED process. You can go for repairing of high structures like turbine blades. Then larger 3D printed parts and multi-material capability. You can also develop the multi-material capabilities with the DED process, and high quality metal parts and hybrid manufacturing capabilities also it is present in the DED technology. Then limitations, low resolution and no support structures. DED does not lend to itself to create a support structure as in the case of powder bed fusion process, but it is a very limitation, another limitation in the DED process. Then low dimensional accuracy. Then application, die repair and refurbishment, thermal management, direct metal products, and surface modification and coatings, aerospace and aircraft component repair, and these are the turbine blades repaired by lens or DMD technology. Then coming to powder bed fusion process, the powder bed fusion is defined as an additive manufacturing in which thermal energy selectively fuses region of powder bed. Here the source is a laser source. Then you can move the XY plotter according to the STL geometry, STL file geometry. Then the laser is moving in a particular direction so that the laser is interact with the powder particles. Then the powder particles are fused and solidified onto the surface so that you can be able to build the components. Then the basic mechanism in laser metal interaction process, when this is a substrate material, then your laser is interacting onto the substrate. So some of the laser is reflected back and some of the laser is scattered and some of the laser is absorbed by the material. Then some of the laser is transmitted through the material. So we need to have the unique property of a material using as a laser as a power should not have highly reflective materials, because if it is highly reflective nature, this whatever the energy is coming from the laser source, that will interact the substrate or powder particles, that is reflected totally. 90% of the energy is reflected back, only 10% of the energy is available. That 10% energy is not sufficient to melt the material, so that's why you need not go for highly reflective materials. So because of the limitation in the highly reflective materials, so people can also do that with coating of some non-reflective materials to the reflective materials, so that the small cavity is formed. That cavity is enough for remaining melting of the material. So you can go back to the transfer in radiant black body. So once the light is emitted, light is impinging on the small cavity, that light is reflected back and forth so that the heat is accumulated. Then we can treat it as a black body. Similarly, the small thickness of the layer, which is highly not reflective nature, that will take care of the highly absorptive material. Then it creates a small cavity. That cavity is enough for the light energies. Laser is impinging onto the cavity, then it is reflected back and forth so that the energy is accumulated, that energy is transferred to the substrate so that the metal is melted. So then there are different mechanisms involved in the powder bed fusion process. Or powder is a feed material for any additive manufacturing process. The one is solid sintering, and second one is chemically induced binding, and other one is a liquid phase sintering and full melting. So what is solid sintering? Just you can see the four particles which are in spherical nature. Just you can combine all the spherical nature of the powder particles, then there is a void. So once you apply the energy to the spherical particles, that energy is absorbed by the spherical particle and going to start necking formation. So this necking formation will continue, and during the sintering process, thus the porous, the cavity is very low compared to initial one. So this is one sintering process used in one of the mechanism powder bed fusion process. Then another mechanism is chemically induced sintering. Yes, you can see an example, laser processing silicon carbide in the presence of oxygen, where SiO2 forms and binds together a composite of SiC and SiO2. Because if you are processing SiC in open atmosphere, because of the presence of the oxygen, that will react with the SiC to form SiO2. the SiO2 act as a binder between the SiC, so to form a composite. Similarly, zircon boride in the presence of oxygen, where zirconium oxide forms bind together, a composite zircon boride and zirconium oxide. And other example is aluminum is in the presence of nitrogen to form aluminum nitrate. So aluminum nitrate particles. So using this as a technology, we can also combine these SiC and SiO2 or aluminum aluminator, so that we can able to make composites very easily. So another mechanism is liquid phase full melting and liquid phase sintering and partial melting. So here the powder separate particles, and you can combine with some coating material which are coated to the particles or added to the particles. When the energy is absorbed by the coated material, that coated material will have low melting point temperature, so that will convert into liquid state and occupied in between the T grains and act as a binder. So that is another mechanism is involved in this process. So now latest this Mark Forging is one company. They are making this type of technology with binders of one filler material, and actual material is another filler material. They are going to join where the laser is focused on the substrate. Then because of the low melting point of the material, that will melted and occupied between the grains of the actual material. Then after that you can do sintering. Then that binder material is gone away because of the low melting point temperature of material. Then the sintering can be happen, so that the parts can be produced very easily. So that is also comes under direct DED technology. Another mechanism is full melting. Because of the high energy supplied to the powder particles, the powder particles are melted and fused together and form onto the substrate, so that you can able to build the component very easily. So this is the powder bed mechanism. So laser is interact with the powder particles with the required geometry. The geometry is taken from the STL file format, so that you can able to interact the powder particles and the laser according to the STL file format. Then after that, just you can add a layer. Then again you can do it like that. You can develop the component very easily. The PBF process of amorphous polymers have been successful. Polymers and metals and ceramic materials also can be used for as a feed material for powder bed fusion process. Then the advantage is low cost, no or minimum support, because the powder itself takes care of the support for small structures, not for large structures. Wide material choice, you can have a large range of materials including ceramic, glass, plastics, metals and alloys. And powder recycling, you can use 30 to 70% ratio we can use for recycling. Then accuracy and surface finish strongly influenced by the operating conditions and powder particle size. This is very important role to get your final geometry as well as properties of the components which are produced through powder bed fusion process. The finer particle size produce smoother, more accurate parts, but are difficult to spread and handle. So larger particle sizes facilitate easier powder processing and delivery, but hurt surface finish, minimum feature size and minimum layer thickness. With the PBF process, total part construction time can take longer than other additive manufacturing process, because of the preheat and cool down cycles are involved in powder bed fusion process, that it takes a lot of time to complete this. Then relatively slow and long print time, post processing required, weak structural properties, surface structure, support build plate and powder recycling, thermal distortion, high power usage. These are the drawbacks in the powder bed fusion process. Then applications, medical, aerospace and manufacturing, automotive industries. Application of PBF recently, the example of this include the PBF manufacturing fuel nozzle of General Electric GE9X engine, which is used on Boeing's 777 aircraft. The GE9X is the largest turbofan engine produced, and additively manufactured nozzle is 5 times more durable than previous versions. So these are the various applications in the form of a chart, part model, and you can get the CAD model, convert into STL file, then either powder bed fusion or direct energy. Then you can use this technology to convert into a solid one. Then application depends aerospace and oil and gas. This is G9X in fuel nozzle. So applications bearing orthopedic implants, medical, and a very high strength to weight ratio, no biocompatibility concerns, and aircraft structural components, commercial aerospace, lightweighting advantages versus similar utilized metal alloys, automobile fuel management system, automated performance, excellent fatigue and chemical resistance properties. Then coming to the combination of additive and subtractive process. So we can call it as a hybrid machining process. It is not a new process. Every additive manufacturing process component you need to go for post processing. So that is a subtractive process. You want to remove the material from the unwanted areas, then finally you can get the correct surface finish as well as good geometry. So here inbuilt the machines are available with additive as well as subtractive manufacturing, so that you can save a lot of time for developing. Now you can remove this DED setup and you can add any milling cutter, so that you can do it in remove the unwanted material from the developed components. Yeah. Now coming to the non-beam based metal additive manufacturing process, here in the previous slides we are using a beam based, that is either laser or electron beam or any arc as a energy source. So that energy is utilized to melting the material and deposit on the substrate, so that you can make a component. The non-beam based metal additive manufacturing, in that one is a friction stir additive manufacturing, additive friction stir deposition, and ultrasonic additive manufacturing. So what is the importance of non-beam based metal additive manufacturing? Here the melting of the material could not be taking place during the additive process of using this technology, whereas in beam based, either melting or partial melting, then you can get the object. So during melting process, some of the materials may react with the environment. That's why you need to provide vacuum environment or inert gas environment. So even if you take care of all these things, there be some materials which are not compatible to between the two materials. It is not possible to produce the additive manufacturing process in different materials with these beam-based technologies. Whereas in this case, you are not melting the material. There is no problem of compatibility of between the two materials. Then you can able to produce the component very easily. Even the materials are not weldable actually. So both friction stir additive manufacturing and friction stir deposition, both are different, not same, are intensive process that involves severe plastic deformation at high temperature. So both the process involves severe plastic deformation that leads to dynamic recrystallisation. Finally, you can achieve grain refinement, so that you can able to generate the components which are having high strength to weight ratio component. However, there are significant difference between them. One is the friction stir additive manufacturing comes under hybrid process, because it is a sheet lamination process. In the sheet lamination process, you can make the sheets with the good surface finish. Then you can go for processing of the sheets, so that you can able to build the components. So that's why initially you can remove the unwanted materials from the sheets and achieve the good surface finish and good perfect matching between the two sheets. Then finally, then you can add additive process, so that you can build the final component. So whereas the other process, that friction stir additive process, additive friction deposition process is completely deposit of the material onto the substrate. The deposited materials is having very low melting point temperature compared to the substrate material or equal to the material. Then you can see the differences, comparison of different solid state AM process, ultrasonic additive manufacturing, friction stir additive manufacturing, additive friction stirrer. Ultrasonic sonator is there. That sonator will vibrate with ultrasonic frequency. That frequency is utilized to diffusion of atoms between the two materials or two sheets, so that finally you can be able to generate the components. Whereas friction stir additive manufacturing, it is also sheet lamination process that we'll going to discuss in coming slides. Then just you can see that the sheet thickness is very small in the case of ultrasonic additive manufacturing, very low, that is 0.1 mm. Then the itself generate is a very costly process compared to friction stir additive manufacturing. Here you can go up to 1.5 mm thickness. Minimum thickness is required for additive manufacturing process. 1.5 mm. This is also not applicable because it is a hybrid process. Here also it requires sheet preparation and additive process. That's why it is a hybrid process. Both are hybrid process, but it's not hybrid process. Then resolution limiting factor, subtractive process, and it is also subtractive process. It is a two geometry is very important role to get the good deposition and improve the quality of the objects which are generated through additive friction stir deposition process. Temperature which are generated relatively low, relatively high, and relatively high. The microstructure similar to pre-processor. The microstructure will not change it before and after the additive manufacturing component because it is energy is developed through ultrasonic additive manufacturing is very low. Only diffusion of atom, that is looks like a solid state welding also. So here you can, because of the dynamic recreation, you can able to achieve equiaxed in the steel zone. Here also you can also achieve equiaxed steel zone. Now this is friction stir additive manufacturing. This is similar to friction stir welding. Then here we are seeing just different layers of equal to 1.5 mm is the minimum thickness. Then you can stack into a particular position. Then just you need to process. Then you need to have a friction stir welding tool. That is a tool with the shoulder as well as a pin. The pin is inserted between the layers. Then you can able to process it. The tool is rotated with a certain RPM. The shoulder is contacted with the top surface of the layer. So because of the rotating and non-rotating member, that heat is generated due to the friction. So that heat is transferred to all the layers. Then that reaches to the recrystallization temperature of the material. Then you can able to move the tool in the processing direction so that the metal is moved from the advanced to the retreating side. Then you can fill the gap so that you can able to generate the component very easily. So just I am showing one video which is related to friction stir additive manufacturing. So all these sheets are stacked into a particular position. The tool is rotating and moving in the direction of processing direction. Then he has taken in next step for processing of all the sheets which are in particular position. Then after that, you can remove the material, and both the combination of additive and subtractive process is used. Now he is removing the unwanted material with the help of a milling cutter. Yeah, this is the final component. So very easy to produce the component within a very short time. Now the basic, the another mechanism is another technology is additive friction stir deposition process. The difference between friction stir additive process and additive friction stir deposition process. Here the feeding material is inserted in the hollow shoulder. Then the shoulder is rotated with a certain RPM. The shoulder is contact with the substrate which is at the bottom of the place. Then there will be contact between the rotating hollow shoulder and the substrate. That heat is generated. That heat is transferred to the substrate and the tool and the material which are going to have in the shoulder. So the low melting point temperature of the material compared to the shoulder, the metal is deposited at the substrate so that we can generate the layer. So the basic between friction stir additive process and additive friction stir deposition. So in friction, this is the stack of all the layers. Then you have a pin and the shoulder. The shoulder is rotated with certain RPM and reaches its requisite temperature because of the contact with the shoulder and the stack of the material. So that leads to increase the temperature and reaches to requisite temperature. At that moment, you can move the shoulder in the direction of processing direction, so that you can able to generate the additive manufacturing components. Only this region. So that you can able to generate a large size. Just you can shift this region to this another region, either left side or right side. Then you can able to generate the bulk size of additive manufacturing components. Whereas in this case, hollow shoulder, you can use a feeding material in the form of a rod. So that rod is solidified onto the substrate material, and because of the low melting point temperature, so that you can able to generate the components. Just you can see the build rate versus accuracy of all the three processes: powder bed fusion process and direct energy deposition and additive friction stir manufacturing. You can have more accuracy and as well as building rate also very high compared to direct energy deposition as well as powder deposition process. So this is the friction additive friction stir deposition process. So how we can develop the composite, or we can develop the additive manufacturing components through friction stir deposition process. So there's 4 steps involved in a particular arrangement. In the step 1, you can able to make a groove. Then that groove length is equal to the length of the pin. Then you can insert the material into the groove. Then you can able to process it. Then after that, then you can go for the second step. The pin length is lesser than the length of the pin. Then you can make a groove. Then you can fill the another material or same material. Just you can process it. In the third step, the pin length is still lower than the second one. Then make a groove which is equal to the length of the pin. Then you can insert the same material or different material. Just you can process it. Then the fourth step, you can able to generate another material which is equal to the same length of the pin, because same procedure you can apply to this one. So like this, you can able to generate the composites in a bulk way or in a smaller scale also. Yeah. So this is one of the scholars' work. He has done friction stir deposition process, develop the functional gradient materials with the silicon carbide volume percentage variation from the bottom to the top. Is a tool A and tool B and tool C. So just he has to apply the same technique which I shown in the last slide. Then he can able to achieve the different volume percent in the thickness direction. So just you can see in the bottom silicon carbide region in region 3 and region 2 and region 1. Just you can analyze the what is the volume percentage of the region 2 and region 3. So in region 1, the aluminum content is like this, and silicon content 14.03 plus or minus 0.3, 12.37 plus or minus 0.6, and 17, and region 2 11 and 10.03 like that, and region 3 6.3. So region 3 is less silicon carbide percentage, whereas region 2 is a little bit higher than region 2, region 3, and still higher than region 1. Yes, you can also conduct the hardness survey for from the top to bottom. then the hardness is varying from the region 1 to region 3. So region 3 is the lower one, and region 2 is the middle one, region 1 is the top one. So top one, you can have either almost 14 to 17% of silicon carbide, whereas region 2 only 10 to 12%, and region 3 only 2 to 6% of silicon carbide. So the variation of the silicon carbide in the variation due to the volume percentage variation from the top to bottom, you can have different hardness from the top to bottom, so that functionally you can vary the properties along the thickness direction, so that you can able to produce the composites or additive manufacturing components. So additive friction deposition is a thermomechanical process. So you can have more number of parameters like shoulder geometry and rotation of the shoulder, and normal force, the vertical force, and filler material, and layer height, and transfer speed. These parameters control the heat flow and material flow. The material flow is very important role in friction stir additive manufacturing, additive friction stir processing, because with that only you can generate the components without having any. The material flow is depends upon so many factors. So those factors are shoulder rotation speed, traverse speed, tilt angle, tool geometry, and vertical force, and so many pin geometry, shoulder geometry is also there. So microstructure formation and applicability to non-weldable alloy is same in both the friction stir welding and processing. A shoulder with a protruding pin is spun at a high rate and inserted into the softened material. The shoulder then traverses the material to either join two interfaces in friction stir welding or treat the surface in friction stir processing. However, in addition, additive friction deposition, there is no pin structure penetrating the base material. The different geometry configuration lead to different heat flow boundary, therefore different cooling rates. So in additive friction deposition, there is no pin because of the provision we can have that feeding material. That's why we don't have any pin, so that the lot of difference in the heat generation. So in future capabilities, the peak temperature of additive friction deposition process normal ranges from 60 to 90% because of the absence of melting. The parts do not suffer from the base issues associated with the rapid solidification, like porosity, hard cracking, elemental segregation, and dilution, aggregation of finally dispersed oxide particles, and dry residual stresses. The low porosity and residual stresses in the as deposited part render post-processing heat treatment unnecessary, although post-processing for surface finish is often required. So this is one of the paper I took from the journal paper. He is able to produce the additive manufacturing components. So this tantalum and niobium coating deposit on the copper substrate, which showing strong mechanical bonding and delamination under bending. So niobium and tantalum is deposited into the copper material. Then you can able to see the delamination of the component. That's why they can do conducting. They can do a bend test, so that there will not be any deal. There will be perfect bond between the two, even though two different materials, different material properties and physical and chemical properties. There will not be any difference between the metallurgical aspects. So what are the advantages? Flexibility in feed material, and the beam-based process have a restriction on feed material in terms of powder composition, shape, and size. So in beam-based, the powder composition, shape, and size will influence the properties of the material. This imposes a great barrier. The powder development of the powders in the nano size and micron level, it is also adding additional cost to the powder bed fusion process. Whereas in this case, the greater barrier for widespread implementation of metal AM. In contrast, additive friction deposition can use solid rod made from a cast or rod alloys as the feed material, because already well-developed technologies are available in casting or rod forging process. With that, you can develop the rod material. That rod material is as a feed material in case of friction stir, additive friction stir deposition process. The scalability, you can find a large scale. You can just, I have shown one video, you can produce a large scale compared to additive manufacturing process. Then what are the benefits with respect to the different categories? One is non-beam and flexible feed material and scalable. So non-beam, because of the non-beam, no melting, low energy, low cost, using that dynamic recrystallization and no solidification, a refined grain size, equaxed grain size, isotropic properties. Then flexibility feeding material, either cast or consolidated powder, you can able to make a powder metallurgy components. Then exploration of new materials, you can add different materials. No hard cracking, low elemental segregation, no aggregation, oxide particles, no non-weldable materials. And the scalable high build rate, large scale parts, ability to repair. You can also repair the structures. So every process has its own advantage, then apart from some limitations. So the limitations in this process, additive friction stir process based on technology has focused on increasing the part size and build rate. As a result, the shoulder and the filler dimensions are large, leading to a large in plane feature size. And in additive friction stir deposition, the deposition path is guided by G-code based hatch pattern. Since algorithms are available to automatically convert the CAD file to G-code, it is straightforward to go from CAD file to part as long as the geometry is put. The printable geometry is limited by the in-plane resolution and maximum overhang angle in additive friction deposition, giving the layer by layer nature of additive friction deposition parts may require additional post-processing to compensate for the stepwise transition at the edge of each layer. Then another issue is in friction stir deposition, the buckling issue. When you do height of the structure is very, very high, then you need to apply vertical force. That vertical force is very efficient, very compulsory in friction stir additive process or additive friction processes. So due to that, the buckling taking place. That is another issue. Then tooling is also an issue because the tool is always contact with the substrate surface. Then a lot of heat is generated. That because of the heat, that heat is transferred to the feeding material, so that always it is exposed to high temperature. Thus you can go for high temperature melting point temperature materials, and the life of the tool is also you can see for the new materials. Then comparison to other solid state process, it is already over. I think the pathways. Widespread implementation of metal AM needs to possess a series of attributes such as affordable to customers, convenience and easy of use, energy efficiency, environment friendly, because this process is environment friendly. So wide applicable to engineering materials. You can weld any materials, non-weldable materials also welded, but in powder bed fusion or DED process, non-weldable materials cannot be possible. If you are combining two or more materials, the metallurgical compatibility should be there in powder bed fusion process or electron beam as a power source. Then compatibility with the major technologies, reliability of part properties. Then coming to the last topic, lattice structures. Lattice structures are unique class of space grid structure composed of the inside struts with certain diameters and angle. So it is a space grid structure have extensive application in the aerospace field due to the combinational advantage of such as lightweight, high strength, high heat insulation, shock absorption, and noise reduction. So many advantages using lattice structures. One is strength to weight ratio you can improve, and you can also heat insulation purpose, and you can also shock absorption purpose and noise reduction purpose. At present, aluminum alloys materials are widely selected to fabricate lattice structure because aluminum alloys are very useful in aerospace and defense components. So that's why we can, because it is having a low melting point temperature, and that's why we can go for making the lattice structures. The traditional, what are the traditional manufacturing methods for producing the lattice structures? The traditional manufacturing methods of metal lattice structures include investment casting, plastic processing method, and combination of extrusion and electrode discharge machining. So with the use of the conventional technology, you can able to generate the lattice structure. However, these methods have high requirements of materials and confront great difficulty in fabricating such kind of complex structures. It limits the design freedom of material and structure of because the very structure is very, very small. So due to that complexity nature, because of that, you cannot able to produce conventional route. In detail, investment casting requires liquid metal to grade fluidity. Meanwhile, it is difficult to manufacture low density lattice structure with topology optimization and complex structures. The combination of extrusion and electrode discharge machining is only used for the manufacturing of pyramid lattice structures. Further, these traditional manufacturing methods have complex technology processes that need to design, mold, and all having high cost. Then additive manufacturing can be used to fabricate lattice structure of any complex form by depositing the material layer by layer, and it has become a new method for manufacturing lattice structure developed in the recent year. So there are present technologies SLM and SCABM used for making the lattice structures. And also another technology we are going to use wire additive manufacturing for producing the lattice structure. So already it is discovered the basics of the wire additive in the last lecture. So I'm not going to in detail in the process wise, but the component wise, yes, you can see the pyramid type of lattice structures. You can able to produce the components. Then you can also see the metal group structure of ER2319 aluminum alloy structure. There is a good bonding between the two grains. Then you can able to produce the components with stronger. Then structure, lattice structure, the scheme lattice structure is one is a struct and it is connected by a node. Then this is a sequence of manufacturing strategy to produce the lattice structure. Thus, first you need to produce the struct, then you can add the node to that, and you can able to build the components. So using this wire arc additive manufacturing, we can able to produce the components very easily. So the first patent in 1920, wire arc additive manufacturing is probably the oldest and only simplest, but least talked about the range of the additive manufacturing process, because at that time it is not well developed CAD, CAM environment and CNC. Then we can integrate with the CAD and CAM and CNC. Then we can able to produce the additive manufacturing components through welding route. So with the resolution of approximately, you can able to generate the deposition rate 1 to 10 kg power depending upon the arc source. You can also go for multiple arc source using this technology. So the main research groups in WAAM technology, China, Holland, United Kingdom, France, United States, India, and Australia and South Korea. There are synonyms of WAAM: welding deposition, welding based deposition, welding based rapid prototyping, 3D welding, 3D micro welding, near net shape manufacturing, hybrid layered manufacturing, shape deposition manufacturing, shape metal deposition, direct energy GMAW based additive manufacturing, the multiple plasma arc welding based rapid prototyping. So this is various welding process can be used: GMAW, gas tensioner, plasma arc, and CHISA pump. Apart from that, CMT also can be used. Then what are the features and energy source? Now I'm focusing on cold metal transfer, reciprocating consumable wire electrode. Typical deposition rate is more than the normal welding press, and also it is deposited in a cold state. Then robotic based includes capable of manipulation system, CAD, CAM, and software. And this is the robotic. Yes, you can see the robotic welding gun is attached to the end of the robot arm. Just you can able to print the component very easily. Yeah, yes, you can see the metal transfer. So the CMT is also integrated with the robot, then we can able to generate the components very easily. Then compared to other welding process, CMT will give more advantage because it gives less additive friction, because the material deposition during the deposition process, the less amount of heat is supplied to the process. That's why we can able to generate the components very easily. Yeah. So some of the materials which are generated WAAM technology. So this is titanium alloy and 4043 Inconel 717. So if you see Inconel 717, this is one layer, another layer like that. So in between the layer, just you can see this, there will be perfect bond between the two layers. So without bond between the two layers, there will not be any having any strength of the components, that loses its properties. That's why the creation of bond between the two layers is very important in any additive manufacturing process. So just you can see the various materials which are used in wire arc additive manufacturing to build the components. There are residual stresses, porosity, delay, deformation, surface finish, and oxidation, crack. One is slide and fifth one is straight. Just you can see the different materials with respect to different properties. The quality performance, TIG, MIG, plasma, wire design, heat treatment, short working, interpass, and post-weld treatments can be do it in wire arc additive manufacturing components. So out of these, CMT is better than other welding processes. If you want to go for small structures, then you can go for pulsed TIG welding process used as a source for wire WAAM. The variables which are used, wire feed rate, voltage, and argon pool and weld speed, is similar to welding process. There is no much. Just I'm focused on the heat transfer, the metal transfer. So the metal transfer is from the electrode tip to the substrate. Suppose if it is a spray transfer, the deposition is deviated from the target place. So if it is a short circuit transfer, the deposition is exactly onto the substrate. So this is possible in the CMT welding. It is not possible in other welding processes. And also you can able to produce the support structures. These are the structures you can able to generate either vertical or a horizontal movement of the link torque, so that you can able to generate the components. So these are the CAD files, and you can generate the components. Due to the gravity, there is some deviation from the exact location. This is support structures, lattice structures, which produced through additive manufacturing, wire arc additive manufacturing techniques. So benefits, already in the last class, one of the speaker has covered applications, 3D printer ship propeller, and then coming to what is 4D printing. So 4D printing is the process through which a 3D printed object transforms itself into another structure over the influence of external energy input as a temperature, light, or other environmental stimulation. So it is similar to 3D printed object, but it is exposed to external power that due to that will changes the dimension. That is known as a 4D printing. So 4D dimensional printing is also known as bioprinting. Active organ or shape memory morphing system uses the same techniques for 3D printing, though a computer program deposit of material in successive layers to create three-dimensional object. However, 4D printing adds dimensions of the transformation over a time. It is therefore a type of programmable matter, wherein after the fabrication process, the printed product reacts with the parameters with the environment like humidity, temperature, and changes its forms accordingly. So 3D printing and 4D printing. 3D printing, just you can supply the material as a feedstock into the system, and you can take the CAD geometry, and you can able to print the structure. Whereas in 4D printing, you can able to generate the smart materials. Then after printing, just you can apply the stimulation to these developed 3D printing component. According to that, it changes the direction and shape. The size changing advantages, the most obvious advantage of 4D printing is that through computational folding, objects larger than printers can be printed as only one part. Since the 4D printed objects can change the shape, can shrink and fold, objects that are too large to fit a printer can be compressed for 3D printing into their secondary form. New materials, new properties, mostly shape memory materials can be used in 4D printing process. Another advantage of 4D printing technology is use of possible applied materials. 4D printing has a vast potential revolutionize the world of materials as we know it today. So applications: self-repair piping system, self-assembly furniture, medical industry, and fashion design. Yeah, that is the 4D printing process. Then coming to 5D printing, the name of this technology is quite misleading since 5D printing does not refer to the addition of fifth dimensions of the printing process. So 5D printing refers to 3D printing using 5-axis 3D printer instead of 3-axis used in conventional 3D printing. 5-axis additive manufacturing essentially builds the object from a multiple direction, thus producing stronger parts than regular 3D printing process. In conventional 3D printing, the object is created by the addition of horizontal layers deposited on the top of each other. With 5D printing or 5-axis printing, the print head is capable of moving back and forth on 2 axes in addition to the X, Y, and Z axis of the 3D printer, hence the total number of 5 axes. You can see the video of 5D printing.
If you're watching this, 5D printing. 5D printing is better called 5-axis printing, where there are 5 distinct axes along with printer heads. This allows for far more complex structures to be printed while also enabling much stronger construction. And Gauri had thought of making a machine that combines additive and subtract.
Only the addition of 2 axes so that you can able to print in particular direction so that this parts is more than the 3D printing components.
In a typical 3D printer, the head moves from layer to layer, depositing a thin amount of extruded plastic, essentially breaking down your object into flat slices and printing. It is moving, and so a completely new 3D printer. But with the 5-axis, since the bed itself is moving, it gives you freedom to print that kind of structure.
So some of the research areas I can explore in these slides. Yeah. So you can also develop the new product, and you can also go for innovation of the kind of objects which are produced through any additive manufacturing technology, because each and every technology has its own limitations. Then you take care of the limitations for developing your innovation kind of objects, and mostly the biomedical applications, dental, paramedical, and biological application. And the new materials which are developed through friction stir additive or additive friction deposition is very easily compared to other additive manufacturing technology. And rapid tooling and rapid manufacturing, because you need to increase the life of the tooling, then you need to go for cooling channels. If the cooling channels is complexity nature, to increase the heat transfer rate so that increase the life of the tooling, So for that, you need to go for additive manufacturing process to develop the complexity of the nature of the cooling channels in the tooling or rapid manufacturing. And the geometric modeling, data exchange, and software issues that you need to take care of from the CAD file onwards to STL file conversion. So many things are there to need to work to get the in the papers. Then process improvements, you can improve the accuracy as well as finish and size and strength. Strength of the additive manufacturing components. The ultimate and strength is very high, but the yield strength is very low because of the porosity structures. So to manage the heat management, and they can able to produce the components with high strength. So strength in terms of yield strength, not ultimate tensile, because we need to take yield strength for design consideration. There is no concern about ultimate tensile strength. Then development of newer process equipment and controls, and development newer application, aerospace, electronic, and aerospace applications, especially electronic and defense applications. Additive manufacturing is a very important area. Then process modeling and simulation issues. You can model the components and you can simulate the component under different AM technologies, and you can see the difference between your modeling objectives as well as your real objectives. Well, is there any difference or any deviation? How the deviation is coming into practice? So with this, I can conclude my lecture. It is open for discussion. Then scaling issue. Thank you for your attention.
So thank you, sir. Kumar sir, it's a very good lecture regarding to the additive manufacturing matter. So if anyone is having the questions, please ask it. And you can also post in chat box.
Sir, can I ask a question?
Yeah, okay.
Sir, I'm Aditya from CBIT. Sir, the question is, can we convert the conventional automated MIG machine into by suitable J codes into this wire arc additive manufacturing process? With
No, we can make it. We can make it, but the heat affected zone in the additive manufacturing in conventional MIG welding process or TIG welding process is more compared to CMT. That's why people are preferred, especially CMT. So during that process of deposition, the heat is not supplied. For that, you can reduce the heat affected zone, and also deposition rate is very high compared to normal MIG welding and normal TIG welding process.
Sir, one more question, sir. In friction stir processing, I did not get the concept how that once the filler material is injected, how the solid state welding is taking place in additive friction stir processing, sir.
So in additive friction, but just you can feed the filler material or deposited material through hollow shoulder.
Yes, sir.
So in friction shell welding, you have a shoulder and the pin, no? So
Yes,
instead of pin,
we-
you have to make a hole which is equal to the diameter of the feeding material. Just you can insert the feeding material into the shoulder. The shoulder is
Okay.
rotated on.
Okay.
So because of
Okay.
the low the filler material, that it reaches to recreation temperature and softens the, and you can give the feed movement to the filler material, which is equal to
Okay,
the
sir.
deposited material. That
Okay,
mechanism
sir.
you can add existing friction stir welding machine.
Okay, sir. But we should wait for it to cool, no, sir, to reach recurrent.
Not necessary. Not necessary.
Okay.
That's why the
Okay.
product compared to powder bed fusion process.
Okay, sir. Okay, sir. Thanks. Thank you, sir.
Yeah, okay.
Sir, good morning, sir.
Good morning.
This is Dr. Prabhakar from KITS Warangal, sir. Sir, good morning. Sir, it's
How
a
are
nice
you?
presentation.
How are you?
Fine, sir. Fine, sir. Fine, sir. How are you, sir?
Okay. Fine.
Sir, it's a good, nice presentation, sir. During your lecture, I have observed, especially fuse deposition and direct energy deposition. I had some few doubts about. During fuse deposition, whenever the powder particles are sintered,
Yeah.
then we have shown the various stages of sintering. That pouring round. Yesterday I also asked about Manjaya sir. Once the pouring round, there will be some distortion or shrinking. Then how to compensate the distortion and shrinking?
Okay, distortion of the total object you are going to talking about.
Yeah, sir. So during pouring round process, once during the generation of the grain boundary, that will be become into small pores. At the time, there is a chance of shrink.
That size of the pore is very, very small compared to the dimensions of the component. Even normally after casting component, we are going to sinter. During the sintering process, there will not be that much of dimensional changes.
Okay. So another one, sir, during this direct energy deposition, how the temperature gradients, there may be influence these temperature gradients on the residual stresses. Is there any no for that also how to resolve that? Because the temperature gradients are not uniform throughout the cross section.
Yeah. So that's why one of the research area I have explained in one of the slide, heat management.
Okay.
So you can manage the heat by external cooling agents, so that you can heat transfer rate can be reduced, so that residual stresses is very low, and also the properties which you are getting the heat management facility, you can get more properties than without management. But residual stresses in the case of direct energy deposition is very low compared to the powder bed fusion process. Because heat is not accumulated much in case of DED process, because heat is transferred to the surrounding immediately. So that reduces the residual stresses which are induced during the process.
Sir. Okay, sir.